This is Geology 100 Natural Disasters. My name is Dr. Scott Nowicki, and this lecture topic is floods and extreme weather events. A flood occurs when a stream's discharge becomes so great that it exceeds the capacity of the existing stream channel. As a result, it causes the stream to overflow its banks and exit the channel. Floods are normal events, and they should be expected over a relatively long period of time. As discharge increases, that means as the total amount of water in the stream increases, the water rises in the channel and erosion starts to scour the bed. A stream profile is a plot of the elevation of the bed of the stream as it goes from the head at the top of the stream to the mouth at the bottom of the stream. It forms a smooth line going from the head to the mouth. And as you can see from this profile plotted on elevation versus distance, that it's steeper at the beginning and it becomes shallower further along the course. So this distance along the x-axis is the distance along the watercourse. The other interesting change that occurs is near the head of the stream. These valleys tend to be V-shaped. They are steeper walled and with a relatively narrow stream bed itself. As you work your way down the stream channel, moving to reach B, the walls are less steep. It is less of a V shape and more of a closer to a U shape. And then finally, when you get down to C, down here near the mouth or near base level, the slope is significantly less, and as a result, the valley walls are significantly less steep. At the bottom of this image is a plot of the width, depth, velocity, and gradient as function of distance along this plot. So going from A to B to C, the width actually increases with distance down the stream. The depth typically increases with distance down the stream, and the velocity, at least to some degree, increases with an increase in discharge. The opposite is the case with gradient, that the gradient starts high and it becomes less and less as you work your way down the stream channel. The definition of discharge is simply the water cross-section, meaning the width times the depth, times the velocity of the stream. So discharge can increase either by increasing the velocity or increasing the total size of the stream. And in the end, what you get is cubic feet per second or cubic meters per second, how much water volume flows down past a point at any given time. So even though a stream may be 10 meters wide in figure A, and it's also 10 meters wide in figure B, by simply having it 3 times the depth, 9 meters in B versus 3 meters in A, there is a whole lot more water flowing through that point at any given time. We also use hydrographs to describe streams, and that means that along this y-axis is the stream discharged in effectively cubic meters per second, and then along the x-axis is time. And a hydrograph simply shows how much flow over time. So if you were measuring in a stream, and over time, as rain starts to fall, it increases the total amount of water flowing, it increases that discharge until there's a peak, and then it decreases over time. Now, this is what's actually occurring within the stream. This is a hydrograph. But what we can also plot on here is rainfall. So here's this rainfall event, this red line showing a lot of water fell as precipitation effectively between hours 2 and 3. And it is that rainfall that actually generated this increase in discharge within the stream itself. The plot of the red is shown over on the right-hand side. This is the rainfall intensity in centimeters per hour. So this gives us an idea of how much water falls from precipitation, and then what does that do to the stream discharge. And in cases where there's a lot of water falling in a relatively short period of time, we wind up with these things called floods. Now it's important to think about the stream itself and the floodplain in which both the streams flow and the floods occur. Most of the time, a stream flows through the stream channel, and along the sides of the river channel are often these levees. They result because streams flow fastest in the middle and they flow slowest on the edge. And so wherever the stream is flowing the slowest is where it's going to deposit material. Now, when a flood does occur, it overflows these levees and then proceeds to spread out over the floodplain. And the floodplain is the rest of the area adjacent to the flood. So this sediment-laden floodwater moves out over the entire surface, and as water leaves the channel, it rapidly slows down and drops all of its sediment adjacent to that channel. Finally, after many floods, successive floods build up these natural levees, dumping sediment closest to the channel, therefore building these walls that tend to hold the stream in. The frequency and magnitudes of floods are highly calculated and averaged numbers in order to give us a pretty good statistical probability of when floods will occur. The reality is we use terms like 25-year flood or 100-year flood, but it doesn't really mean that a flood will occur every 25 or 100 years. That means that over an extended period of time, these types of floods occur on average within every 25-year period. So the probability is one 25-year flood on average occurs every 25 years. But the reality is that two 25-year floods could easily occur within the same year. Or you could have a long period of time during which no 25-year flood occurs. You could have 100 years with no 25-year flood. So how often a flood will occur and the magnitude depends on the river. Predicting a flood for the future requires a good record and statistical analysis over time. The best record is the longest record that we have. Here is a plot showing the annual maximum discharge, so how much water is flowing, over this recurrence interval or years. So you can see that relatively small floods, small discharge events occur rapidly. And very large discharge events occur very seldomly. So this plot simply shows discharge over this recurrence interval, meaning how often these things occur. So here would be our 100-year flood. It's somewhere around between 2,500 and 3,000 cubic meters per second. Any given year, there's a 1% chance that this kind of flood will occur. Thus, it is a 100-year flood. And a 50-year flood, somewhere around, again, 2,300 cubic meters per second, has a 2% chance every year. Thus, it is a 50-year flood. Now, one interesting thing that we as humans have been doing to these natural systems is we've actually been increasing the total amount of impermeable surfaces. So here's a cityscape showing lots of pavement, lots of places where water, if precipitation falls, it will accumulate and flow down the streets, down the channels, rather than infiltrate into the water, into the subsurface or into the soil. This effect of urbanization is actually increasing the likelihood of floods. So we've got hydrograph A and hydrograph B showing effectively the rainfall and flood that occurs before urbanization on a natural surface. And then down here in part B, we've got what happens after urbanization. So hydrograph A shows the typical lag between when the rainfall occurs and when the stream floods. So here's our rainfall, and it takes a couple of hours for this rain. And then here's the change in discharge in a stream. So there's our hydrograph of this stream flow. You can see that the rainfall occurs, and then there's a lag time, and then there's a peak in the flood, and then it takes a while for this to then decrease. Now, hydrograph B shows this decrease in lag time because in urbanization, with channelizations of streams and paving over surfaces, the rainfall occurs at the same amount of time, but the peak in this stream flow, meaning the flood itself, increases, it both gets higher and occurs quicker than during a natural event. What this is suggesting is that urbanization is actually increasing the likelihood of streams to flood, at least on the local level. In 1993, the Mississippi Basin was subject to a historic record-setting flood and was probably the most costly flood in modern history, certainly within the United States. The reason why this flood occurred was in part due to humans, the fact that we've been changing the landscape of the floodplain, and then second, that it was just an extremely wet year. There was a lot of precipitation that had fallen the previous month, and during this event that occurred in July, a lot of water fell within a relatively short period of time. So as that water was working its way down the channel, there were levees in place that held it, and increased the likelihood of flooding further downstream. And really, the thing that was missing was the ability for water to flow out of the stream channel higher up and move into these floodplains. So in the end, the floodplains that were in the kind of central Illinois down to St. Louis got completely inundated. Now, the Mississippi itself is a big system. There are a lot of stream tributaries that feed into the Mississippi River, suggesting that, well, if water falls anywhere within this drainage basin, it can affect floods that occur on the main trunk of the stream. Here's what it looks like when a stream, and especially the Mississippi, floods. Here's the normal stream channel held within its banks, flowing down through a floodplain. And when the flood occurs, that stream channel is still full of water, but the natural levees aren't able to hold it in, and so the water flows into these floodplains as it should, as it has many, many times in the past. But what has changed is that, of course, there are farms and homes and cities that are now built within that floodplain. So these events, like the 1993 Mississippi flood, are common throughout the world. In China, there are events that occur on a regular basis that flood these cities to an equal degree. So a series of floods in central China in 1931 is estimated to have killed at least 500,000 people and is probably the most deadly event in the 20th century. These events keep occurring, and as humans move into these floodplains, as they move in more tenuous situations, the likelihood that these events will continue is very high.